Okay, everybody, here's day 2 for 3-1, and 3-1 is all about line symmetry, this part 2. So we're going to talk about the definition first. We'll go through some graphs, and then we'll make sure that we get some good examples for points and for equations. All right, so for line symmetry, the definition is 2 points, P1 and P2, that are SWRT, that means symmetric with respect to a line L, very creative again, if and only if L is the perpendicular bisector of P1 and P2. So that means if I'm drawing a line segment between P1 and P2 to be a perpendicular bisector, think about what that means. So bisect means to cut it in half, and bisect at a 90-degree angle means perpendicular. So we have perpendicular bisector. So for every pair of points on your graph, you're going to have that relationship. So it's going to have the 2 points cutting it in half and then being a 90-degree angle. So as we look at these different graphs where this is true, where you fold over a line, like those capital letters we talked about before, we want to think about, do translations, if we move the graph, what happens to those symmetry lines? We know that they affect symmetry points. We talked about that depending on the transformation, but we need to talk about what happens with the lines as well. All right, so let's take a look at a couple quick graph examples. So y equals x squared, you guys are really familiar with that parent graph, our regular old parabola. I'll make a sketch here. Great example, kind of the poster child for line symmetry. So what line is a parabola symmetric with respect to when it's just x squared? Well, it would be the y-axis. So I'm going to go ahead and put that in. That's my line L. That means any point on my parabola, L will be the perpendicular bisector for that set of points. So it will fold over that line. And it's named, surprisingly enough, the line of symmetry. So that helps you keep track of that. Now I want you to think about what happens if you translate this graph up or down. So say I added 3 or subtracted 3. If I move the graph up or I move the graph down, would it still have the same line of symmetry? And the answer is definitely yes. It's still folding on the y-axis. But if you moved it to the right or to the left, then that line of symmetry moves with the graph. It would no longer be symmetric with respect to the y. Still has line symmetry though. So realize translations definitely do affect where those lines of symmetries are. Okay, graph number 2, our friend the circle. If you have a circle with the center there, where would the lines of symmetry have to be? Well, there's lots of different lines it could be, right? As long as the line goes through the center, you're going to be able to fold over that line and have an image that looks exactly the same on both sides. So kind of the short story on this one is it's symmetric with respect to any line through the center. So circles are one of those kinds of graphs that have both point and line symmetry, as long as the point is the center and the lines go through the center. So that's one of those types of graphs. All right, so just like we did with point symmetry, there are some common points that we look at, like the origin specifically. Line symmetry works the same way. There's 4 lines that we talk about which have symmetries that are important to look at in graphs. The 2 axes, and then y equals x and y equals negative x. So the x-axis symmetry is if you have the point xy, then you also have to have the point. And now think about what happens. If you flip something over the x-axis, which part of the ordered pair would change? Well, think about where the x-axis is. So if you're above the x-axis and go below, that would be x-axis symmetry. The y value would have to change. So it would have to have x negative y as well. So to be symmetric with respect to the x, you would have to have both of those ordered pairs on the same equation. All right, for y-axis symmetry, very similar. If you have the point xy, then you're going to need to have, all right, now think about y-axis symmetry. If you have a point on one side and the symmetry point on the other, what would change the x to the y? Well, it'd have to be the x. So you'd also have to have that point, opposite of x, y. So both of those points would have to be on your graph. So the x changes sign. All right, the next one, y equals x. If you have the point xy, then, okay, y equals x is the identity line, like the points 1, 1, 2, 2, 3, 3. So when you're thinking about on a graph, y equals x would be this line right here. If you're going to have points that flip over that, so one on one side and one on the other, what ends up happening is their x and y interchange. Then y x. So if you have the point xy, you also have to have the point yx. In the identity, they're equal, so they're interchangeable. All right, so then the last one, y equals negative x. If you have the point x comma y, then you need the point. And let's see if we can figure this one out. So as a picture, line y equals x means this one right here. So we have a point on one side, we want to flip it to a point on the other. Not only do they have to interchange position, they also have to be opposite in sign because of that opposite there. So it's opposite of y, opposite of x. So they switch places and they're opposite. Okay, so I want you to see some point-by-point examples of what this would look like. So I have a chart included for you in your notes. We'll probably also get a little handout one as well, but this at least gives you the idea kind of all in one place, even including the origin, all the different symmetries we look for. All right, so let's take a look at pairs of points that could represent this. So I'm going to take a look at a few points here, which ones have origin symmetry and kind of on down the line. Why don't you take a second and pause the video for a moment so you can go through and complete these first on your own. And if you can add y equals negative x symmetry at the bottom, that would be great. That one kind of got erased off the bottom here. What I want you to do is look for points that have these symmetries. So which pair of points, using that little guide to help you, which pairs of points have these symmetries? And there could be more than one as well. So go ahead and pause and then fill that in and then jump back in. All right, so here are the different symmetries. So origin symmetry would be the pairs A and D and C and E. So if we look at origin symmetry, that's where you can draw a line segment through and there's a point equal distance on the other side. And that's where both ordered pairs, both part of the ordered pairs have to be opposite. So we have +5, +2, -5, -2. That's a good example. And C and E are the same thing. X and Y both change signs. So that's origin symmetry. All right, next one down, x-axis symmetry. There's a couple pairs of points here. We could have used A and E or C and D. Either of those would be fine. So A and E going from here to here, the Y changes sign, and same thing for C and D. Okay, y-axis symmetry, same idea. Let's take a look at that one. So for y-axis, I had, looks like A and C, and then also D and E. So looking at the different pairs there, the x value is changing sign as you flip from one to the other. Okay, y equals x symmetry. I did put the line y equals x right on your graph for you. It's that pink line. So if you flip over that, what has to happen is that you have to have your x and y values switch. So xy has to become yx. And if you look up here on your graph, you have the point 5,2, and then you have the point 2,5. That line L is the perpendicular bisector between those 2 points. So the pair A and B would be your y equals x symmetry. All right, last one, y equals negative x. That would be putting in this line right here. And we need to find which points would have that relationship. So y equals negative x. So not only you switch locations, the x and y, but they're both opposite. So look at the point B, 2, 5, and then look at the point down here, -5, -2. Reversed and opposite. So B and D would be your pair for y equals negative x. All right, let's start from scratch once and see if you can do it that way. So I'm going to give you this point, 4, -3. Go ahead and graph that. So 4, -3. That's our original point. What I'm going to have you do again is stop the video and try this. Graph the point that would be symmetric with respect to the x, the y equals x, and y equals negative x, and the origin. So 5 more points. Show the coordinates, the xy pair, and what symmetry it is. So you can really know that you understand what's changing as you have these symmetries. So go ahead and stop the video, do your points, and then check back in. Okay, so here are our points. So if we want to do, let's do x-axis first. So that means the y changes sign. So we'd be at the point 4, 3, and that would be x-axis symmetry. Okay, if we're going to have y-axis symmetry, we have to flip across the other way. So that would be -4, -3. So that means the x changes sign. All right, y equals negative x. So that means the x and the y in the ordered pair just flip places. So it would be -3, +4. So -3, +4 would be y equals x. Excuse me, and think about putting in that dashed line, y equals x, It'd be that one, and you would fold over. So from quadrant 4 to quadrant 2. Okay, y equals negative x. That means not only do they reverse, they're the opposite. So it would be positive 3, excuse me, positive 3 and negative 4. That would be y equals negative x. So that would be going through, here's the line y equals negative x, folding from one to the other. Excuse me, got my nice little fall cold going on here. All right, so my last one, origin symmetry. That's where both x and y are opposite in sign. So negative 4 and positive 3. So negative 4, positive 3 would be origin symmetry. So we can look and see what all of those different symmetries do. Okay, well again, what if you have infinitely many points? You don't want to have to do that for every single point. So we have to be able to deal with what it looks like for equations. So for the equations, we're going to look at and see if we can recognize what the equation is. If we can't, then we have to go ahead and do kind of some proving like we did before for our other graphs. Okay, so let's take a look at this graph and see what happens with this. So if you know what it looks like, fantastic. If you don't, you should be putting it into your graphing calculator so you can take a peek at the picture. But x squared plus y squared equals 9. That's x squared plus y squared equals r squared. That is a circle. And it's centered at 0, 0. And the radius, based on that equation, would be a 3. So that's the picture that we're talking about. So a circle centered at the origin with a radius of 3. You can see that on your graphing calculator if you just go ahead and solve your equation for y. Now don't forget, you square root it, even root, plus or minus. And you can go ahead and put it in on your graphing calculator. Now the goofy thing is that you have plus or minus, you're going to have to type it twice. So if you take a look at mine, you're going to have to type it in there twice. So go ahead and pause and put it in if you need to. What I did, if you put it at negative 10, 10, and you graph it, it doesn't really look like a circle. It kind of looks more like an ellipse. But that's because your screen is longer than it is tall. So if you want to make things look square, do zoom number 5, and it will actually look like a circle. Okay, so just gut check here. Do you think it has those symmetries? X, Y axis, y equals negative x in the origin. Well, it sure looks like it folds over the x and the y equals x, y equals negative x, and definitely the origin, because remember, circles have point symmetry at their center, and look where the center is. It's at 0, 0. So kind of the short answer to this question is, well, yeah, it has all those symmetries. But what we'd have to be able to do is actually show that with a proof. So I'm going to go through all of them with you so you can see how that works. And if you have that little table, this will really help you. So x-axis symmetry means the y changes sign. So what you have to do is plug in negative y into your equation and see if you get the same relationship back as the original. That would mean both the original point and with the opposite of y are both on that graph. When you simplify that, well, that gives you exactly the same statement as what you started with. So it definitely has y equals or x-axis symmetry. Now let's try y-axis. In the y-axis symmetry, the x changes sign. So we have to replace the x and see if we get the same result back as our original. And sure enough, we do, which tells me that yes, indeed, this has y-axis symmetry. All right, we're going to do the same thing for the next two. We'll do y equals x. In y equals x symmetry, the x and y change places. That means I substitute an x and a y in the opposite spot, so that means I just switch them. So I'm putting y in for x and x in for y. Do you get the same relationship? Well, sure, it's written in the other order, but that's equivalent. And then y equals negative x. Not only do you switch their position, you take their opposite sign as well. And look at what happens here. Same as the original again. So I know that it has all 4 of those lines. Those are all yeses. Okay, last one to double check is the origin. Origin symmetry is where the x and the y both change sign. So if the x changes sign, the y does too. All right, well, look what happens when you do that. Oops, that's supposed to be a plus. Same as the original? For sure. Yes, so it has all 5 of those symmetries. Now, of course, most of your graphs probably won't have all 5, but this is a great example to show what happens if they all work. So we just have to go through that list and prove it. It's a little bit more work the more you have to prove it for. Okay, last thing we're going to talk about today is just categorizing a little bit based on what type of symmetry a graph has. So we have these functions that are called even and odd. And even and odd means they have very specific symmetries. So if you're going to be an even function, that means you are symmetric with respect to the y-axis. Now, the easiest examples we have of that is looking at polynomials. So let's talk about just polynomials specifically. In polynomial lingo, that means all even exponents. Now, there are other graphs that are going to be even that have y-axis symmetry, but most of the graphs that we're dealing with right now are polynomials. So we want to know what that means too, all even exponents. So let's go ahead and look through the list. What I'd like you to do is look for all of these that have all even exponents. So those are going to be ones that are even. Graph them on your calculator too, so you can look at each one as we talk about it. So pause if you need to and graph it and kind of look at it, and then we'll talk about them. So for the first one, y equals x squared, that's our poster child for y-axis symmetry. This is definitely even. All the exponents are even. Okay, go ahead and graph the next one. So pause if you need to. This one has all even exponents, so it's a 4 and a 2. And if you look at the picture, the plus 5 just moves the graph up 5. Still has y-axis symmetry, still even. Okay, graph the third one, so go ahead and pause if you need to. Now, when you take a look at this graph, it doesn't look like the last two. There's not y-axis symmetry. This is a no. And if you can look at the equation, I wonder if you can figure out what part of the equation makes it not even. And hopefully you're focusing your attention right there. The 3x has an odd exponent, so by definition, it is not even. It's still a polynomial, but it doesn't have y-axis symmetry, not even. Okay, graph the last one. So go ahead and pause if you need to. What does the minus 3 do to your graph? Well, it takes that parabola and shifts it down 3. But does that still have y-axis symmetry? Sure. So that is even. It has all even exponents. So I want to direct your attention to this plus 5, that minus 3. These constants. What constants do is they shift your graph up or down. That does not affect y-axis line symmetry. So you may want to make a note for yourself that constants are okay. Now for polynomials, we can see that pretty clearly, but another even function, if you take absolute value of x, that's a great example of an even function. That has y-axis symmetry, right? It's a V shape. If you move that graph up or down, it would still have y-axis symmetry as well. So in general, constants are okay for even functions. All right, so if we have even, there must be odd, right? If you had to guess, if even has all even exponents, odds are going to have all odd. So for polynomials, we need all odd exponents. And let's talk about what symmetry they would have. Symmetric with respect to, look at the poster child for odd functions, y equals x cubed. Go ahead and graph it on your calculator if you're not sure what it looks like. So pause if you need to. But the graph looks like this. We did x to the fifth too, would be the same sort of thing. 1, 1, negative 1, negative 1. Okay, so what symmetry does that graph have? Well, it's symmetric with respect to the origin. So odd functions have origin symmetry. They both start with O, if that's helpful to you. So odd origin. So when you look at origin symmetry, we know what that means. The x and the y both change signs. So for polynomials, that means all odd exponents. Okay, so let's take a look at the examples down here. So go ahead and graph it. Pause if you need to. So x to the fifth plus 2x, definitely odd. Both odd exponents. Next one down. Trouble on this one. When you type it in, look at right there. We have an even exponent, so that is one of those neithers. It's not odd, it's not even either. Because of that even exponent, we do not have origin symmetry. Okay, be careful on the last one. Look at this. What does a minus 3 do to your graph? Well, it takes that original top graph that I had right there and it shifts it down 3. So it still has point symmetry, but now where's your symmetry point? Right down there. So does it have origin symmetry? No. So it is not odd. It still has symmetry, but it's not the origin. So maybe a note for yourself. No constants. Constants are not okay in an odd function. All right, so we talked about polynomials. I just want to show you one other really good example of an odd function would be that graph y equals 1 over x. I just want you to have another parent graph in your head. That's the one that looks like this. Definitely has origin symmetry, right? So if you take any point, go through the origin, you reach a point on the other side. Great example of odd. And again, if you move it up or down, you're no longer going to have origin symmetry, so it wouldn't be odd anymore either. So in general, no constants on an odd. Okay, so that pretty much wraps up line symmetry for you, and we'll be moving on to parent graphs next.